Good morning, everyone. Welcome back to our googology course. Apologies for the inactivity this past 2 weeks. I've been busy with many other things. Today we'll be learning about Bauer's extended array function. And as usual, the materials that I use, I will kindly attach them in the description. So it's the usual. Let's just get started then. In the last video, we learned Knuth's up arrow notation. And this allowed us to create really fast growing numbers. Say 3 double arrow 3. We may break this down into 3 arrow 3 arrow 3. That is 3 to the power of 3 to the power of 3. So now we have a power tower. Break down the power tower into 3 to the power of 27. And that is approximately 7 trillion. Now you get my point on how fast it grows, right? In one of our recent videos, we also covered Graham's number in part 1.5, which is G64. Which is basically 3 with G63 amount of arrows to 3. Okay? And that's a little brief of what we learned in the past videos. Now let's learn BEAF notation for real. Start with A with curly brackets, N and B. This equals to A with N amount of up arrows to B. So this is how it's written in Knuth's up arrow notation. But this value, it can also be A with n minus 1, A with n minus 1, n minus 1, A, B amount of times. So that is the basics of BEAF notation, the absolute basic. Say if I have 5, 2, 2, that's going to be 5 with 2 up arrows to 2. We can say it's 5 to the power of 5. That's going to equal to like 3,125. I'm not sure. Okay, now on to the next thing that I want to talk about. A double brackets 1 and B. This is also another basic. It means you have brackets like these. So you can think of it as a nesting. This occurs B amount of times from the start point or end point to the center point. That means if you have, say 2, 3, 2, that is going to be 2, 2, 2. And another one. This is because the same logic is applied from the absolute basics that we started with. Which is that if we have A with double brackets to N, in the basics it was single brackets, but we can do double brackets now with the logic. So it should be A double bracket N minus 1, N minus 1, A. And that is going to happen B amounts of times. So this is something that occurs a lot in the BEAF notation. And in the BEAF notation, this is what we call expansion. So when we're in double brackets, that's called expansion. Now let's go to triple brackets. A triple brackets N B. That is equal to A double bracket A double bracket A double bracket A dot dot dot. Wait, sorry, this isn't N, my bad. It's supposed to be 1. So you have this to A and this happens B time from the start point or end point to the right on the center point. So it's the same thing but with more brackets. In BEAF notation, we call this explosion. And so on for the more brackets you add. Now let's write it like this: A1DB. D is a superscript. So we have A with D minus 1 brackets to A D minus 1 brackets and so on, right? So it's going to look something like this if I write it out this way. And it's for B amounts of times from the starting point or the end point to the center point. Now let's rewrite that to A1 D and B. So now we have rewritten everything, right? And they equal each other. This is where we've gone into linear arrays. So linear arrays look something like this, and let's get a brief of how we break them down. Say you have 4 variables, A, B, C, and D. You can break them down into A, comma, B minus 1, C, D, C minus 1, and D. But hold on, this is only the occasion where B and C are greater than 1. So you can't just go around using this for everything. Because if B is 1, then the rule of A1 with a superscript of D and B will apply if B is equal to 1. Because that's what we learned in the absolute basics, right? Now what if we add more variables? A, B, C, D, E, F? It might look like a mess when we try to break it down, but trust me, it's easier than what you think it is. A comma B minus 1, C, D, E, F. As you can see, the pattern just continues like that. There's nothing we have to change unless B or C are greater than 1. So in reality, this is actually easy. Once you finish that, B and C have to be greater than 1. Okay, now let's go look at entry conversions. This is where some entries can be converted so that it may be simpler for us to evaluate. For example, if I have 5 variables, A, and A, it might look hard to try and evaluate, right? So now we're going to rewrite it as A, 2, 1, 1, 1, and 2. That's going to make it a bit easier. Now what if there's an entire array nested in that? So a comma a comma a comma a comma a. Then there's one entire array in here. What is this defined as if we rewrite it simply? Well, my homies is defined as a, 3, 1, 1, 1, and 2. So that is basically how you can evaluate these. Okay, now say if I have b minus 1 layers of this, what's it equal? It should equal to a, comma b, comma 1, comma 1, dot dot dot. That means it goes and so on and so forth until it ends, and 2. So that is how you can convert entries to further generalize it and simplify it. Let's get to the next topic and a new expression that I want to introduce you to. Our next topic is multi-dimensional arrays. So what do I mean when I say multi-dimensional arrays? That means our arrays have reached multiple dimensions, basically. Now, if I write b ampersand a, what's this equal? So Jonathan Bowers defined this as a comma a comma a comma a and so on for b amount of times in an array. And I'll give you a little example before we go any further into multidimensional arrays. This topic is, I think, a bit complex for some people, but I promise you can wrap your head around this once I finish teaching you. 3 ampersand 3 is equal to this. So we see that this is b and this is a. So there should be 3 3s in our array. 3 3 3. We can say this is 3 angle bracket 3 and 3. So 3 with 3 up arrows to 3, that is equal to 3 triple up arrow 3 equals 3 double up arrow 3, double up arrow 3, and double up arrow 3. So it's 3 double up arrow 3 double up arrow. Okay, my bad. I added that one extra there, sorry. So it's 3 double up arrows 7 trillion, which is insanely large already. That is how fast our new expression grows. Let's go back to our arrays, shall we? If you have a, b, with a subscript of 2, it's just equal to b ampersand a. Now what's this? Add one more to our subscript. A, b with a subscript of 3. It's a comma a comma a comma a. For b times with a subscript of 2, it's growing really fast now. Yeah. You get it, right? It's growing really fast. Now, let's go to the generalization. A comma b with a subscript of n is a comma a comma a comma a and so on b amount of times with a subscript of n minus 1. So it grows stupidly fast. Yes. Let's go a comma a comma a comma a. So we say that this has b amount of things in it, right? Now what if the subscript is an array itself? So this has B amount of things too. This has B amount of things too, and so on for B amount of times. We can rewrite this simply into A comma B with a subscript of 1 comma 2. And it is insanely fast growing. Now, A comma B comma 1 comma 3. No, with the subscript of 1 comma 3. I slipped up, my bad. I think writing it like this would be inconvenient, so let's define this big A as A dot 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 for B amount of times. So it's A with a subscript of A with a subscript of A with a subscript of A, and so on. Two and 2. That means this has got a subscript of 2. This has got a subscript of 2 as well. So the more you add, the more subscripts it's gonna have until you reach the top layer. Now what if that 1 at the first subscript was a 2? So AB 2 comma 2, that is equal to A comma A comma A comma A dot 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 for B amounts of times with the subscript of 1 comma 2. Now we generalize it. A B with a subscript of n comma 2 is equal to A dot 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 B amounts of times and with the subscript of n minus 1 comma 2. Okay, now you may ask, what if I add another subscript in there? So 3 comma 2 comma 1 as the subscript, right? That we can rewrite it as having a row break in between. This is where it actually gets fun. This right here, my homies, is the dimensional array that I was talking about. When first introducing you to this topic, you may not have understood what I meant by dimensional array, but you will now. This right here is our main function, and this right here is the subscripts in our function expression. Okay. Now I want to introduce you to X structures. Say we have X. X with an ampersand to n is equal to an array of n's for an n amount of times. Now x plus 1 ampersand n is equal to n for n amounts of times with a row break, and you add 1n here. Now x plus 2 with an ampersand to n continues our pattern. So we have the same exact thing here, right? Our row break is the same as usual, but see that? We add another n in it. This goes on until we reach 2x and n, which will equal to x ampersand n with a row break and x ampersand n. Okay, I think you probably get the idea now. So what's 3x ampersand n? I'll give you some time to think about it. That's right. It's x ampersand n with a row break, x ampersand n and another row break to x ampersand n. Okay. What if we go to x squared? How does that work? Of course, you think the pattern will continue, right? And you're in fact right about that. It's going to be x ampersand n with a row break to x ampersand n with a row break to x ampersand n, and so on. For an n amount of times. Now what if it's x cubed? So this becomes x squared ampersand n. This becomes x squared ampersand n2. Everything becomes x squared ampersand n. We are now just applying the same logic over and over again. And this is usually how most array notations work. And I would say this is pretty similar to Bird's array notation if it weren't for the fact that this row break is equal to this in Bird's array notation, if I remember correctly. But that's for the next part. Let's focus on our main topic. So it goes on forever, right? That's how X structures work. So for the people who have been watching this the entire time and wondering, are we just stuck with 1 as that row break? And the answer to that question is no, we're not. So AB with a row break of 1 and add another row break with 2. That is A ampersand B with a row break to A ampersand B. Alright, that's a nice generalization. But we may actually write it in a simpler form. So what happens when we keep adding row breaks? A, B, row break, row break, row break, row break for B amount of times. That we have moved to the new dimension. So we've moved on to planes now. A ampersand B, A ampersand B. For every new row that I start, that is 1 row break. So let me write the row breaks in. This is our plane, 2D. This is when you add it for B amount of times. You can rewrite it into A comma B with a row break of 2 to 2. And that is equal this 2. Okay. Now you should get the idea, right? We add more to it. So now we should have 2 planes. So let me poorly draw these planes in. Yes, this is 2 planes. You get the idea. Or like this. You could keep adding planes. So much so that you go into the realm, which is AB with a row break of 3 to 2. This is when you've reached realms, or the 3rd dimension. Alright, that's what we call the realm, then the pattern goes, and so on. So now, it's a flume, the fourth dimension. And you can just keep going and keep going and keep going. So now you have A comma B in the nth dimension to 2. How can we grow our function on from here? If you remember the commas in our subscripts, yeah, we're applying the same logic to our dimensions. So if we have A comma B with a row break of 0 comma 1 to 2, that is an x to the power of x structure. Fascinating, right? Now what if it was O and P to 2? That, my homies, is x to the power of px plus O structure. Then you can stack the parentheses. So A, B with the row break of 1 and 1 to 2, that is x double arrow 3 structure. So if you keep stacking those parentheses, you eventually get to the point where it's A, B, dot dot dot, 1, dot dot dot, 1, 1, 1, dot dot dot. Yes? So something like that. And it's to 2. That is an x double arrow 2n minus 1 structure. And I forgot to say, there are n amount of 1s in this one expression. Okay. So that's all for dimensional arrays. Let's go to the final topic of our video. From what we've learned so far, we have A ampersand B, row breaks, expansions and explosions. We rewrote the arrays to make linear arrays. And a lot more, right? This is where we are nearing the limit of BEAF notation. So let's look at legional structures. A legion will be defined as L. And we're going to introduce the new operator A black rhombus to B. This is equal to A ampersand A ampersand A ampersand A for B amount of times. Let's give you guys an example. If we have 3 with the black rhombus to 4, that is 3 ampersand 3 ampersand 3 ampersand 3, because we are supposed to have 4 3s in it, right? So 1 2 3 3 ampersand 3 ampersand 3 ampersand 3. So once we actually try to break this down as 3 comma 3 comma 3 ampersand 3 and ampersand 3. Now we can rewrite this 3 black rhombus 4. It's going to be rewritten as 3 comma 4 with the slash operator of 2. This isn't to be confused with division, okay? Because we're in googology, it's not the same. Alright, now, what have we got? A b with the slash operator to 3. That, my friends, is equal to a black rhombus b with a slash operator of 2. So a comma b with the slash operator of n is equal to a black diamond b with the slash operator of n minus 1. That will be the generalization. Okay, if you have a this to b with the slash operator of a this to b, it's a 2L structure. You can add more, make 3L, 4L, 5L, 6L, and so on, right? That's another generalization until you get to an XL structure or an X squared L structure where it's now a plane. Now, if you have those same legional structures, dot dot dot, for b times with the subscript of a comma b, that is L2, or we call it a legion. Alright, so we have legions, right? That pattern continues on. So b a comma b, that is L3, and these are called legends. You can go L4, L5, L6, and so on until LX. You can even do LL, LLL. Heck, you can make them arrays if you want. And that is the limit of BEAF. Alright, so that is all that we will be covering today. So, part 2's over. I'll see you in part 3. And I hope you understand what I taught you. Materials that I use will be attached in the description. So, bye bye.